This lesson is beginning on page 10 of the matrix packet, and it's regarding inverses of a matrix. So if A is a square n by n matrix, if there exists an n by n matrix called the inverse of A, then when you multiply A by its inverse, or the inverse by A in either order, you will end up getting the identity matrix. So we'll see that happen in some examples down here. A little bit of vocabulary. Not every matrix has an inverse. It has to, first off, it has to be square, but even if it is a square matrix, meaning 2 by 2 or 3 by 3, it may not actually have an inverse. If A does have an inverse, it's said to be non-singular, but if matrix A has no inverse, it is called singular. There's a quick check so that you don't have to go through the steps of actually trying to find the inverse to figure out that it doesn't exist. If the determinant of a matrix is 0, then it is singular, meaning it will not have an inverse. So if you check to see what the determinant is, if it's 0, then there's no inverse to find. Here, on this example, you are given a matrix and its inverse. We will learn how to find the inverse, but for now we're just going to check to make sure that supposedly if I multiply this matrix by this matrix, I'll end up getting the identity matrix. Remember, the identity matrix we learned in the last lesson is that. So you could check to make sure that the determinant, we know that this inverse exists, so we don't have to figure out whether this is singular or not, but you can see quickly that the determinant 3 minus 2 is not 0, so there is in fact an inverse matrix. So I'm going to fill these in here. 3, 1, 2, 1, 1, negative 1, negative 2, 3, and supposedly we'll get the identity matrix if we multiply this. So 3 minus 2 is 1. Row 1, column 2 will be negative 3 plus 3. Beautiful. Row 2, column 1, 2 minus 2. Oops. 2 minus 2 is 0. And negative 2 plus 3 is 1. Beautiful. And as you, most of the time the order of multiplication can change the product, but in this case, supposedly we will also get the identity matrix if we do these in the opposite order than what we just did. So let's double check that. Row 1 times column 1, 3 minus 2. Row 1, column 2, 1 minus 1. Negative 6 plus 6, negative 2 plus 3. So these two matrices are inverses because if I multiply them, I get the identity matrix. Now, finding the inverse of a matrix is a little bit trickier. There's some steps written out here. As usual, I think it might just be easier to show you by example than trying to run through what all those words mean. So let's go ahead and try it. The idea is that I put the matrix that I want to work on here. I want to find the inverse of it, and I put the identity matrix next to it. So this is 2 by 2, so this is 2 by 2. And now I'm going to do to this matrix whatever it takes to make this into the identity matrix. So luckily I already have a 1 here, so I don't have to change that. And to start off with, I am going to try to get this to be a 0. So I'm going to go ahead and keep this first row, and then write down the row operations that you could do to make this be a 0. Well, in this case, not too bad, I can just add these two together. So row 2 here gets row 1 plus row 2. 1 plus negative 1 is 0. 4 plus negative 3 is 1. And then you just do the same thing to this. So 1 plus 0 is 1. 0 plus 1 is 1. Now, This is looking pretty good. This is a nice, fairly simple example to start off with, but to get this to be a 0, I'll need to take this, nope, sorry, this row, this bottom row is good, but this top row, I want that 4 to be a 0. So I'm going to take row 2 and multiply it by -4 and add it to row 1, and that will replace the row 1. So here, looking at this, if I multiply 0 by -4, I get 0, and add it to 1, I get 1. If I take 1 and multiply it by -4, I get -4, add it to 4, and I get 0. Now I have to keep going here. -4 plus 1 is 3, and -4 times 1 plus 0 is -4. This row is good to go, so I don't need to change it. And I'm done. This is the inverse. So then use row operations to obtain the identity matrix here, and that will give you the inverse matrix here. So my inverse, if A is equal to this, then I just figured out that A inverse is equal to 3, -4, and 1, 1. And we could check it. If it is in fact the inverse, when I take 1, 4, -1, -3, and multiply it by 3, -4, 1, and 1, I should get the identity matrix. So 3 plus 4, I got something wrong here, where is it? -1, 3, 3, -4. Oh, this is a -3. Somehow I messed this up. This is -3. So let's go back and figure out what I did there. So, oh yeah, there it is. So it was row -4 times row 2, so that's -4, plus row 1 is +1. So -4 plus 1 is -3. All right, so doing this check was super helpful because I had missed that little negative sign there. So now I'll have -3 plus 4, which is 1, then -4 plus 4, which is 0, then +3 minus 3, and +4 minus 3, 1. And then you could check the other order, but I think we should move on. So if you were finding the inverse of a 3 by 3 matrix, then you've got to do the same kind of thing. Take this 3 by 3 and the 3 by 3 identity matrix, and then perform a bunch of row operations so that this matrix changes into the identity matrix. And that can get a little tedious, so I kind of gave us some hints up here to move it along and make this go a little bit more quickly. So this one implies that the first row is good to go. -1, 0, 1, 0, 0. And then to get the second row here, I'm going to take the first row and multiply it by -1 and then add it to the second row. So -1 plus 1 is 0. +1 plus 0 is 1. 0 plus -1 is -1. And -1 plus 0 is -1. 0 plus 1 is 1. 0 plus 0 is 0. To get the third row, it's going to be negative 6 times row 1 plus row 3. And by doing that, multiplying this by negative 6, then this will end up being 0 when I add those two. So I know that one will be 0. Then negative 6 times negative 1 is 6, plus negative 2 is 4. Then negative 6 times 0 added to the negative 3. Negative 6 times 1 is 6 plus 0. Negative 6 times 0 plus 0. And negative 6 times 0 plus 1 is 1. All right, next we need this to end up becoming a 0. So that makes sense to add these two together. So this 1 plus negative 1 is 0. Negative 1 plus 0 is 0. Negative 1 plus 1 is 0. 1 plus 1 is 1. 0 plus 0 is 0. The second row doesn't change. And the third row is negative 4 times row 2 plus row 3. So negative 4 times the second row, which is written right here, plus row 3, and it goes into row 3. And I'm losing my patience with this, so I'm going to go through and fill them in. You are probably losing your patience also. And then the next thing, I'm getting closer here. I'm trying to create the identity here. The only thing that is missing is that I need this. I messed something up here. This was supposed to be a negative 1 when I added these two together. I do want it to be a 0, but I need one more step to get it to be a 0. So to get this top row, I'm going to add row 3 and row 1. That will keep this to be 1, this to be 0, and that to be 0. And so I'll get my 1, 0, 0 that I'm after. And then if I add row 3 and row 1 here, I'll get negative 2, negative 3, and 1. And then here I'm adding row 3 and row 2. So that's 0, 1, 0, which is what I want there. And then if I add row 2 and row 3 here, I get negative 3, 1. And this bottom row was already good to go. So obviously finding the inverse of a matrix by hand could be very tedious. So the matrix is invertible, and the inverse is this. And you could check it if you take this matrix and our original one and multiply them together. We could do row 1 times column 1, negative 2 plus 3 plus 0. And you would get a 1. And then a 0, 0, 0, 1, 0, 0, 1. So let's avoid having to find the inverse of a matrix whenever we possibly can, and show that it would be very nice and doable on a calculator. So you would do second matrix, edit, and if I want a 3 by 3 matrix, and I'm going to do 1, negative 1, 0, 1, 0, negative 1, 6, negative 2, negative 3. And then go to matrix, math. Somewhere on this list will be the inverse. Come on, it's got to be there somewhere. Oh, it's not on that list, but I know where it is. It will be to do second matrix. We want matrix 1, and we want the inverse of it. And I think I can just raise it to the -1 power and press enter. And then we get the inverse, -2, -3, 1, -3, -3, 1, -2, -4, 1. Phew, glad I remembered how to do that. You could also find the determinant of the matrix, and I think that is on the matrix menu. I don't think I'd shown you that in a previous video. There should be one here that, oh yeah, the determinant. Look, it's so important finding that determinant even though you don't know why yet. It's the first one on the list. So I pick that off, and then I have to go back to matrix to grab matrix A. And the determinant is 1. So here's a shortcut here for finding the inverse of a 2 by 2 matrix. Ooh, that's a good little shortcut. So what we've been doing is kind of doing a Gauss-Jordan elimination to find the inverse of a matrix. But it's a little tricky. Here's a shortcut for finding the inverse of this. It says that I can just do 1 over the determinant of the matrix. The determinant of a 2 by 2 is quick. That would be -3 minus a -4. So -3 minus a -4 is -3 plus 4, which is 1. And then times dA, so these two switch places. And the C and the B stay where they are but become opposite signs. So if this is 4, now it's -4. If this is -1, now it's +1. So that is a shortcut for finding the inverse of a 2 by 2 matrix, which is a lot less work than what we did here. This is the same matrix, and here was our inverse, and there's the inverse with the shortcut. So there's one good application of the determinant. And last thing for this lesson is to use the idea of an inverse to solve a system. So if you had this system and you wrote it as a matrix, then keeping it just a 3 by 3 rather than a 3 by 4 is a nice little application of the inverse that says if you have matrix A times some matrix X is equal to B, then if we multiply both sides by the inverse, then this A inverse A, using the associative property, I can multiply these two together first. This side stays the same. And A times the inverse of A is just the identity matrix. And so this will be X is equal to A inverse B. So if I were going to solve this matrix A, and X being the solution to the equation is equal to B, then I can take the inverse of, so I've got the inverse of A goes here, and we can find that on a calculator. It ends up being 7/4, 3/4, -1, -3/4, -3/4, 1, 1, 1, -1, And this is the answer that I want to get, 3, negative 3, 2. And then this matrix will give me the solution to that. So let's see how that would work on a calculator. So say you were solving this system and you would make this matrix the 3 by 3 and get 1, 1, 0, negative 1, 3, 4, 0, 4, 3, and we would find its inverse and multiply it by this, so we'd need another matrix. Edit. This one is 3 rows, 1 column. Oh, look, it's already in there from a year ago. Then we can get the answer to this system by taking second matrix A inverse multiplied by second matrix B. And there's our 1, 2, negative 2. It's the same idea as if you had done like a reduced row echelon form, but the idea is that you are using the inverse of a matrix to solve a system, and just an interesting different method of solving a system. But you have to be able to find the inverse, and if you're going to find the inverse, you're going to use a calculator. If you're going to use a calculator, you probably would just use reduced row echelon form. But anyway, something else, maybe there's another purpose to the inverse that you will need to know at a later class. Thanks for watching.